Okay. Nth roots, radicals, and rational exponents. So a lot of things in this section are going to be about rules and setting us up. We're going to be doing a lot more computation when we get to 4.2. So what are all the real cubed roots? So I'm going to underline real cubed roots of 27. We're going to talk about how many roots there are and then how many real roots there are for the cubed root of 27. If I'm talking about cubed root, I draw a radical with a 3 in the index position. Now, we're not used to seeing a number there, right? When we do a square root, it's assumed to be a 2, but we don't actually write the 2. But if it's any other number, we have to write that number in there. So this little 3 is in the index position. So remember, that's called the index. So we're looking for the cubed root of 27. Now, the cubed root of 27 is also asking what to the power of 3 is 27. So if I were to take some number in here, well, I know 3 cubed, 3 times 3 times 3 is 27. Therefore, the real root of 27 is just 3. Because I can take 3, multiply by itself 3 times to get 27. We need to talk about the difference between real roots and all roots. Now, the real root is 3. But there's 3 non-real roots for this equation. And we're going to go over a little bit of the why. So, if I were to have an equation like x cubed equals 27, and I were to solve for 0, which means I'm going to move the 27 over, this is something that we learned how to factor back in topic 2. We did difference of cubes. So if you remember the pattern of factoring difference of cubes, it's when I have a perfect cube minus a perfect cube. And that factors to, in this case, x minus 3 times x squared plus 3x plus 9. I know that's digging back in our memory just a little bit. Now, similar to what we've done in previous section, when I have a factor times a factor is equal to 0, then either one of these can be 0. Set each factor equal to 0. Now, I'm not going to go through the whole process, but x minus 3, this is going to give me a real root. Right, I can set x minus 3 equal to 0. Add 3 to both sides, I get x is 3. Good. That's the one we already found. This other factor right here, x squared plus 3x plus 9, I'm not going to go through the process of doing the entire quadratic formula, but this one right here is going to give me 2 imaginary roots. I'm going to change that. 2 complex roots. They might be imaginary, but complex covers more. So the equation x cubed equals 27 has 3 answers. One of them is a real root. 2 of them are complex roots. This today is just asking, what is the real root? So all you have to do is recognize what to the power of 3 is 27. I don't need you to be able to do this part right here. I just want you to understand it for now. Example 2. What are the real fourth roots of 256? If I were to write that with algebraic terms, that would just be the fourth root, where 4 is the number in the index of the radical, of 256. So I'm going to give you, I don't know, about 30 seconds. You should have a calculator out. And I want you to try to find what to the power of 4 is 256. Play with some numbers. If you're looking for like to do the fourth root on your calculator, it can look different ways. So on my physical calculators, the button looks like the X root. You have maybe a calculator that's like this. If you've got a graphing calculator, it's in a menu. It's under the math menu. So if you have a graphing calculator, you would go to the math button and then down to the one that says X root. And you would need to plug that number in. So depending on what version calculator you have, you've got to tell the calculator that you want the fourth root. When you correctly plug this in a calculator, fourth root of 256, you should get 4. So play with your calculator and make sure that you can get it. Figure it out for whatever version you have. You guys figuring it out? You're finding it? Okay. So now your calculator's only going to give you half the story. Because, yes, it is true that I can put 4 in here. 4 to the fourth power is 256. It is also true that I could plug -4 in and get 256, and your calculator is not going to give you that information. So this is where our knowledge of taking roots really comes into play. So the answer, the real roots, are -4 and +4. Now, if I'm taking the fourth root, then that means there are 4 roots total. 2 of them are real. That means the other 2 are complex, and I'm going to show you why. Oh, side note, how many roots total? 4. Because I'm talking about the fourth root. But here's my why. So if I have x to the power of 4 is equal to 256, I'm looking for what to the power of 4 is 256. I solve that for 0 just like I did above. So I subtract the 256. And then I factor. Well, this is a difference of squares. This factors to x squared minus 16 times x squared plus 16. A difference of squares because I have a different subtraction of a perfect square and a perfect square. And this is a unique scenario because when I take the difference of squares and I factor, this is actually the difference of squares again. X squared minus 16 is another difference of squares. So that is further factorable. Now, only difference of squares is factorable. Sum of squares is not factorable for real roots. So x plus 4 and x minus 4 will give me 2 real roots, namely -4 and +4. And then x squared plus 16, if I were to solve that, I would get imaginary roots. Now I've got 2 different scenarios. I have the third root and I have a fourth root. My third root only had 1 real root, namely 3. My fourth root had 2 real roots, 4 and -4. So right way down here at the bottom is a summary. If I'm taking the even root of something, then I will have plus and minus. If I am taking an odd root, like the third root or the fifth root, I will only have 1 root and it'll match. So if this is positive and this is positive. So let me move that up so you could jot that down because that's an important note. If I have even roots, I have 2 real roots. I have a positive and a negative. So if I'm taking the fourth root or the sixth root or the eighth root, if I have an odd root, like the third root, then I get 1 real root. And there's a table there for you to jot down. And the table is really to summarize and go over practice for how to write things from radical form to exponent form. So review from Math 2, but expanding on it like we do in Math 3. Okay, so when we look at an example for numbers, in radical form, if I were to write the cubed root of 25th squared, if I write that in exponent form, the index becomes the denominator. So the 2 stays, the 2 in the exponent stays, and the 3 becomes the denominator. I have 25 to the power of 2/3. Sometimes I can simplify these and sometimes I can't. An example of a mixed example with numbers and variables. So if I here, when I don't have an index written on this radical, it's automatically a square root. It's assumed to be a 2. So I have the square root of 45x to the 5th. Now that means I have to take the square root of 45 and the square root of x to the 5th. The exponent on 45 would just be a 1. And then since 2 is the index, that's going to become the denominator. So this is 45 to the 1/2 power times x to the 5/2 power. Now, when I'm talking about the rule, it doesn't matter whether my exponent is in the radical or outside the radical. It has the same exact effect. These are equivalent statements. So saying the b root of x to the a is the same thing as saying the exponent of all, and well, let's restate that. The b root of x all to the power of a. Those are equivalent. Doesn't matter if a is the exponent is inside or outside the radical. I would rewrite that with a in the numerator and b in the denominator of a fractional exponent. So just an opportunity to review, a little practice. So going from radical form to exponent form. This is 16 to the first because I don't have a number there. So when I rewrite that as a fractional exponent, I'm going to have 16 to the 1/3 times x to the 4/3. So if I go straight from radical form to exponent form, that's how I could rewrite this. It's equivalent. Now, if I could take the cubed root of 16, I would. The cubed root of 16 is some irrational number, so I can't do it. And then on the other one, when I work backwards, in exponent form, I have a to the 3/4 times b to the 1/4. They have the same denominator. That denominator is going to become the index. And then I'm left with inside with a to the 3rd, b to the 1st. I'm not going to write a 1 over the b. So to go back and give one more example, I said that you can't take the cubed root of 16 to get a nice pretty number. So if this problem is the cubed root of 8, well, hopefully you recognize that the cubed root of 8 is just 2. So when I were to rewrite this, I'm not going to leave it as 8 to the 1/3 because I know the cubed root of 8 I could just rewrite as 2. So a little bit of computation and evaluating, right? We know the cubed root of 8 is 2. So instead of writing 8 to the 1/3, I would rewrite that just as a 2 because it's a nice whole number. That would be simplified. And then x to the power of 4/3. I know it's been a year, but you did this almost a year ago in Math 2 because we're about to do it right now. Sometimes it's hard to remember. All right. So simplifying expressions. You did this before also, but we have a new rule that we need to incorporate, and that's this absolute value rule. So we're expanding on it. Let's simplify A, and then we'll come back to this rule. So I'm looking for the 4th root of x to the 12th, y to the 8th. Sometimes it's easier to write it in exponent form to see what I need to do. So I'm going to go slow here. I'm just going to rewrite it in exponent form. That would be x to the 12/4 times y to the 8/4. I just changed my exponent and rewrote it. And then I'll simplify and finish it off. $12 divided by 4, oh, well, that's just 3. 8 divided by 4, that's just 2. That's almost the complete answer. Now there's this rule, and I want you to take it for face value today. We're going to dive into it more on another day on why it works. But the rule says that the even root of x to the even power, when it comes out as odd, I have to use these absolute value brackets. And the short reason is because I don't know whether x is positive or negative. So to cover all options, when this is an odd number, I'm going to use absolute value brackets. So I'm looking for the even root of an even exponent that comes out odd. For example, even root 4, even exponent 12 gives me an odd result. So what I need to do is I need to put that term in absolute value brackets. It's not even the whole term, that piece of the term. And again, I know I only gave you a short version of the why, but we'll go deeper into it another time. Now, the other part, I have the 4th root of y to the 8th, so even root, even exponent, but I get an even result. No absolute value brackets. B is the square root. Okay, cool. Square root of 25. Boom, I know that one. If it makes you feel better and you're like, oh, I want to write the 2 in, you can. It's not common practice, but you can write it in there if it helps you. And then I would rewrite as x to the power of 9/2. and y to the power of 10 halves. Now 10 halves is just 5, so if you want to skip this step, you could just do 5. I'm going to leave 9 halves because I can't, it doesn't go in evenly, and I'm not going to leave it as a decimal, right? My fractional exponents will always be left as one fraction. So I'm never going to turn it mixed. I'm never going to make it into an exponent. And then this is y to the 5th. Do I need to use my rule? Even root, even exponent, odd result. Even root, even exponent, nope. Even root, even exponent with a 10, and I get an odd result. That means I'm going to put just that base and that exponent in absolute value brackets. How are we feeling about this? Feel okay? All right, so example C is the third root of negative 8 x cubed y to the 9th. Excuse me. Now, the square root of a negative number is imaginary, but the cubed root of a negative number, I can do that. Because negative 2 cubed is negative 8. Negative times negative times negative. So the cubed root of negative 8 is negative 2. Beautiful. X to the power of, I have an exponent of 3 and an index of 3. And then y to the power of an exponent of 9 and an index of 3. You don't have to do the in-between step if you can just do in your head. That's fine. That leaves me with negative 2x to the power of 1. 3 divided by 3 will give me 1. And then y to the power of 9 divided by 3 will give me 3. I'm not concerned with any absolute value brackets this time because I'm taking an odd root automatically. Not a concern. Solve each equation for all real roots. 2 more problems. So we know that we practice a lot of skills, and the whole point is to get to the solving every time. That's what really matters. So here's very 2 basic solving with some different exponents. Now the instruction says for all real roots. The problem 5x cubed equals 320 has a total of 3 roots. But it's only going to have 1 real root. The problem of 162 equals 2w to the 4th is going to have 4 total roots. But only 2 of them are going to be real. So I solve. All right. Step 1, isolate whatever's to the exponent. So I'm going to divide both sides by 5. That leaves me with x cubed is equal to 320 divided by 5 is 64. To get x by itself, I take the cubed root of both sides. Now, your calculator will give you the real root. It will not give you all of the roots without you knowing more information. The cubed root of x cubed is x. The cubed root of 64 is positive 4. So this is the real root. There are two other roots, but they are either imaginary or complex. For B, I want to isolate whatever base is to an exponent first. So we divide both sides by 2. Gave you nice, pretty numbers here. 81 is equal to w to the power of 4. And if I'm trying to get rid of an exponent of 4, I want to take the fourth root. So I will take the fourth root of both sides. Now, reminder, when I take an even root, just like when I take square roots, I get 2 answers. Your calculator will only give you 1. So it's important that you recognize this. The fourth root of 81, right? That question is asking what to the power of 4 is 81. It could be 3, and it could be negative 3. Now that only gives me the real roots. There's 2 complex roots also, which we're not going to get into finding today, just the real ones. So that wraps up this introduction lesson. You have an opportunity to practice before we move on to the